Hi, my name is Majd Costa. Today I'm going to present our work on maximizing the electromomentum coupling in piezoelectric composites. We will start with a little preview and motivation. As we know, a wave is basically a movement of energy. Hence, by controlling the wave propagation, one can control also the movement of energy in the structure. One way of controlling the wave propagation is based on metamaterials. So, what is metamaterials? Metamaterials are materials that offer a man-made property that cannot be found in nature, such as negative mass density and negative refraction index. Many researchers have engaged in designing frequency filters and waveguides, as you can see in here, and it was shown that Willis materials can also contribute to this phenomenon. So what is Willis materials? Willis materials are metamaterials that offers a meta-coupling between two fields. So if we consider, for example, one piezoelectric material, its consecutive relation would be like on the one on the left-hand side, where, for example, the momentum is coupled to the velocity through the mass density. And the Cauchy stress tensor is coupled to the strain and the dielectric potential. So the consecutive relation has many zeros. But if we consider an effective material that is equivalent of at least 3 piezoelectric composites, its consecutive relation wouldn't have zeros, but for example, the average momentum would be also coupled to the average strain through the Willis coupling denoted by S, and it is also coupled to the average dielectric, the average electric potential through the electromomentum coupling denoted by W. So in this schematic illustration, we can see an example of a natural coupling between the elasticity and the electrostatics field, which is called the piezoelectric coupling. But we can also see a meta-coupling, which is the Willis coupling that couples between the elasticity and the dynamics field. And our work focuses on the electromomentum coupling that couples between the dynamics and the electrostatics field. Now, Willis coupling has been investigated and optimized, and it was shown that theoretical upper bounds can be reached, where the optimal design exhibit contrast within the geometry and the material properties. And in here, we give an example to see that the value of Willis coupling increase where the asymmetry in the structure also increase. Our work aimed to optimize the electromomentum coupling, which has not been done before. So we aim to optimize it for a one-dimensional structure that has a periodic cell, as one can see in here. So first, we need to evaluate the electromomentum coupling. This was done using the PWE method, the plane wave expansion. It's a method, it's a homogenization scheme that exploits the periodicity of the structure, utilize the Fourier transformation and Bloch theorem. We expand the governing and the constitutive equations, revise them in a way, and until the end, we got a concrete formulation of the effective properties. So one can consider the PWE as a method that takes the microstructure properties, and following the PWE, we obtain as an output the macro structure properties, which was the basic idea of our optimization scheme. So we can consider now that if we adjust the microstructure properties, we can get different values of the macro effective properties, which led to the first optimization problem that has been considered in here, where we aim to optimize the choice of 3 materials out of a table of 10 candidates and simultaneously optimizing the length of each layer. This design is applicable and might have important contribution to future applications. And in here we present the optimal design and also a comparison to a naive design to show the efficiency of the process. We also note that the optimizer, which is GA in this case, seeks for contrast in the structure, as PMMA, the middle layer in here, has the lowest mass density and the lowest piezoelectric coefficient, where on the other hand, the other 2 materials have the largest mass density, the second largest mass density, and also the largest piezoelectric coefficient. And the contrast is not only in the material properties, but we can also we can see that we have a contrast in the geometrical properties, as we can see that the middle layer is relatively short compared to the other two layers. And the next results has been obtained using a gradient-based optimization. And to do that, of course, we need a sensitivity analysis. The sensitivity analysis was computed analytically. And as has been said before, PWE takes the microstructure properties, and we can consider it as it is a Fourier coefficient as a function of this macro property, denoted by Z in here. And following the PWE, we obtained the electromomentum coupling, W, as the function of the same macro properties, Z. So if we insert as an input the derivative of the Fourier coefficient, which is a very easy task to do, and follow the PWE step by step, the same procedure, we can also obtain the sensitivity of W with respect to the same material property, Z. And that is what we did in our model. In this cycle, you can see an explanation of the inverse homogenization that we have done. At first, we will start with the micro property. Using PWE, we can evaluate the value of the electromomentum coupling and also the sensitivity of the electromomentum coupling with respect to any property. Once we have the sensitivity analysis, we can update the design using the MMA method and obtain a new macro properties, a new design. We follow the same cycle until the optimal design is obtained. And the first problem that we consider is length optimization. And here we aim to optimize the electromomentum coupling over the length of each layer, while the total length of the periodic cell and the materials are fixed. We observe that the optimal design has a relatively short layer compared to the other two. And this very specific short layer has, once again, the same property that has been found before, which means the lowest mass density and the lowest piezoelectric coefficient. We can also say that because we have a one layer that is relatively short, design change that is considered suitable for the design variables might be too liberal for the third layer, and divergence may occur. Therefore, a conservative move limit has been considered, which in both cases was 0.03 millimeters. We also observe that for each maximum W with a positive sign, exists an equivalent minimum W with a negative sign, but shares the same absolute value. Therefore, the application of the optimization didn't include the absolute value sign, because we know that for each maximum value, we can also define a minimal problem. So once we know, for example, for the first composition that it has a negative value of the electromomentum coupling, we aim to minimize it, because we know that following certain steps, we can also find the equivalent design with a positive sign. We also addressed the same problem with a graphical solution. And we can see that the same optimal design with the same value has been obtained. And moreover, we can also see that in the second composition, the problem itself in its nature has several local minima, which might hinder the optimization process. And to overcome that, we evaluate the value of W at 20 random points. And once the optimal region is found, from that point, we apply the MMA method until the optimal design is obtained. Now, the next problem that we considered, we unleash the physical constraint between the material properties, where we aim to optimize W over the material properties and the length of each layer simultaneously. This will give us a theoretical upper bound on the value of W and establish a rule of thumb on the optimal design. And to ensure that we obtain a meaningful result, we apply an upper and a lower bound on the material properties. And these material properties was normalized following this upper and lower bound. As we can see in here, the optimal design exhibit contrast within the material properties. We can also observe that we got 4 equivalent design, and in here we show only 2 of them. these both designs are equal in the same value of W and the same sign of W. We also note that intermediate values has been obtained only for the piezoelectric coefficient of one layer, which is the first in here and the third in here. To examine this non-intuitive result, we evaluate the value of W versus every possibility of B, the piezoelectric coefficient, while the other properties are fixed to the optimal design. And we can see in here that indeed the optimal design lies at in between values and not at the boundaries. And finally, we can also say that the optimal design has a homogeneous stiffness, which will also be discussed in the next slide. So to show the contribution of the optimal design on the balance of momentum, we evaluated the momentum ratio with respect to the mass density momentum, pre and post optimization. And we can see that not only the electromomentum coupling is with the same magnitude now as the Willis coupling compared to the pre-optimization design, but also that both contribution has increased by 3 orders of magnitude, which is amazing in my eyes. Now, to examine the sensitivity of W, we applied once again FMO, but now with fixed equally divided periodic cell. And we can see that both results are close one to each other, which means that optimizing the electromomentum coupling is more sensitive to the material properties rather than the geometrical properties. This can be seen in a comparison between these two lines. So with that being said, and in order to study the influence of the parameters of the objective, we optimize W with prescribed fixed properties. For example, in here, we optimize the electromomentum coupling over piezoelectric coefficient and mass density. The other properties are fixed and equal for each layer. And in here, we can see finally the 4 equivalent designs that has been discussed before. One can be obtained from another by flipping the value of the piezoelectric coefficient. You can see it in here, and opposing the values of the mass density. One goes to the 0 and 0 goes to 1. These two steps together give us the same value of W with the same sign. If you consider only one step, for example, these two designs in here, one step gives us the same absolute value, but with a negative sign. And of course, we can see again that we got intermediate values of piezoelectric coefficient, which has been examined and proved that it is true. We did the same process for other couples of properties. And in this table, you can see a conclusion of all the results that we have obtained. We highlight in here 2 rows or 2 lines, you can see it in here, where we also note that if you optimize it over BA and rho or BAC and rho, the results are not far away from each other, which means that the sensitivity of W with respect to the material stiffness is not significant. And we also note that we try to do the same process for any couple that includes C, the material stiffness, but that didn't lead to anywhere, which means that breaking the symmetry of the stiffness or optimizing the electromomentum coupling over C, the material stiffness, is not enough to produce the electromomentum coupling. So with that being said, we still want to search for the best optimal applicable design. And to do that, we take the result that has been obtained before from the discrete material choice and optimize it over the 2 properties that can be synthesized, which is the material stiffness and mass density. And from that point, we can go anywhere because the structure already has a contrast within it, and it has already a value of W. And in here, you can see the optimal design where once again, the stiffness is homogeneous and the mass density is exhibit contrast. To conclude, we can say that optimal design exhibit contrast, but not full contrast. The sensitivity with respect to the material properties are not uniform. Material properties are more significant than geometrical properties for the electromomentum coupling. And we also proved that the electromomentum coupling had the same contribution as the Willis coupling. And we have proved that applicable design gives value of W that are not far away from the theoretical upper bound.